Welcome to another video on turning effects of forces. In this video, we'll be discussing the principle of moments. The principle of moments states that when a system is at equilibrium, the sum of clockwise moments at any point is equal to the sum of anti-clockwise moments about the same point. And this can be shown using this equation. So if you've never seen this symbol before, it simply means sum of. So sum of. So the sum of clockwise moments, so force times distance, recall from the earlier video that force times perpendicular distance is the moment about a point, and this is the sum of clockwise moments, and by the principle of moments we say that the sum of clockwise moments is equal to the sum of anti-clockwise moments about a certain point. So for example, say we have a beam balance over here, and the balance is uniform, which means that the weight of the beam is right at the center. So if my pivot is put right at the center, we can imagine that the beam would be perfectly horizontal, because the sum of clockwise moments is equals to the sum of anti-clockwise moments. So now if I put a box on this side with a weight of say 10 newtons, the anti-clockwise moments would be greater than the clockwise moments, and the beam would tilt towards the left, rotate leftward, anti-clockwise. And to balance this, I would put a 10 Newton force on the right side as well, so that the anti-clockwise moments is now equals to the clockwise moments. And we say that this system is at equilibrium. Okay, now that we have the basics out of the way, let's attempt example 4, which says that a non-uniform rod AC, this is the rod, it weighs 10 newtons, and because it's non-uniform, the 10 newtons doesn't come straight from the center. Instead, it's somewhere either on the left or the right. It's balanced using a string at B and a counterweight of 20 newtons. Okay, and because there is no weight on the left side, we can assume that the center of gravity would be between A and B. Okay, and that's what we need to find, the distance of the center of gravity from point A. And as earlier identified, it's between A and B as opposed to between B and C, because we will need a anti-clockwise moment to balance out the clockwise moment produced by the 20 newtons force. Okay, so let's just point somewhere, say maybe this is the weight, and this distance here, let's label it as D, and this will be 1.4 minus D. Okay, and to apply the principle of moments, we have to identify a point or a pivot. So in this case, we will take moments about B, and by principle of moments, so taking moments about B by the principle of moments, write this out in full. The sum of anti-clockwise moments is equals to the sum of clockwise moments. Okay, and the anti-clockwise moments in this given example would be the weights, so force times distance, perpendicular distance equals force times perpendicular distance. For the anti-clockwise moments, the force, which is the weight, is given to be 10 newtons, and the distance is 1.4 minus D. 1.4 minus D. And the force, or the sum of clockwise moments, which in this case the force is 20 newtons and the perpendicular distance is 0.6 meters. So 20 multiplied by 0.6. Okay, and solving this, you get 14 minus 10D equals to 12 And so D would be equals to, D is equals to 0.2 meters. And recall we defined D as the distance between A and the center of gravity. So center of gravity is 0.2 meters away from A. Okay, so that's all for example 4. Let's move on to example 5, which says that two workers P and Q are carrying a uniform beam of weight 1200 newtons. So because this is a uniform beam, let's redraw this diagram as a beam where the weight is located right in the center, and the weight is 1200 newtons. So 1200 newtons from the center. The length is 4 meters. Okay, 4 meters. P is standing at 1 meter from one end. So this, let's call this pivot here P. And P, this distance here is 1 meter. And the Q is standing 0.5 meters. So here is, so that's a little long. Let's call this 0. Let's call this guy Q, and it's 0.5 meters from this end. Okay, and what is the force on each of their shoulders? Okay, so to approach this question, the first thing you have to realize is that P and Q are both applying an upward force on the beam. This is because the weight is the only downward force acting on the beam, and to balance this weight, P and Q have to apply an upward force so that the weight doesn't drop, right? So that the beam doesn't drop. So these two guys are applying upward force, and let's label Q's upward force as FQ and P's upward force as FP. Okay, next, recall from an earlier example. This example, that if your line of action cuts right through your pivot, then your moment would be 0 because the perpendicular distance is 0, right? So to approach this question, since we have two unknowns, we want to simplify our lives and remove one of these unknowns by taking this point here as the pivot. Okay, so because this force runs through the pivot, then we can say that this, if we're taking point Q as our pivot, then the moment of force Q is equals to 0. And in that case, the only moments we are taking into consideration would be the moment due to the weight and the moment due to the force P is applying. So taking moments about Q, or taking Q to be the pivot by the principle of moments, the sum of clockwise moments equals the sum of anti-clockwise moments, and the clockwise moments here is taking Q as the pivot. The clockwise moment we can see is just the weight, which is force 1200. So force times perpendicular distance equals force times perpendicular distance. So the force is 1200 newtons, and the perpendicular distance is, the whole bar is 4 meters. The distance here would hence be 2 meters. And because Q isn't right at the tip, he is 0.5 from the end, so this distance will be 1.5 meters. So 1.5. This force is equals to force of P, which is what we're trying to find, Fp, multiplied by the distance from this pivot, which is, here is 3 meters. 3 meters minus 0.5, so it would be 2.5. So 3 minus 0.5. And solving for P, you would get Fp equals to 720 newtons. Okay, so now we have Fp. Now we need to find force of Q. To do this, we repeat the same steps, except now we're taking moments about P instead of about Q. So, taking moments about P by the principle of moments. The sum of clockwise moments is equals to the sum of anti-clockwise moments, and always write out your formula and then do your substitution. Okay, so now we're taking moments about P. So the forces, the moments are the moment caused by force Q and the weight. So this is the clockwise moment and this is an anti-clockwise moment. Okay, so the clockwise moment is force Q multiplied by the distance here, which is what? 0.5. The whole thing is 4 meters. Take away 0.5, take away 1, so it's 2.5. 2.5. This is equals to the anti-clockwise moment, which is the force of the weight, so 1200 multiplied by, what is this distance here? This distance here is 2 minus 1 meter. So this is equals to 1 meter times 1. So solving this equation, you get force Q equals to 480 newtons. Okay, so for questions like this, recall that because force Q plus force P, upward force, is equals to downward force, we can double check our work by making sure that Fp plus Fq is equals to the weight or the downward force, which is 720 plus 480 equals 1200 newtons, which corresponds to the weight, and so we can double check that this is the correct answer. Okay, so final example for this video, example 6. The barrel, this is a barrel, it has a weight of 1500 newtons, and so the downward force from the center here is 1500 newtons. Next, it has a radius of 0.5 meters and it rests against a height of 0.2 meters. So this is the step of 0.2 meters. Okay, and what is the smallest horizontal force through the center that is required to push the barrel over the step? So for this, we will be applying the principle of moments, and to do this, we need a pivot point, right? So for this example, the pivot point would be right over here because that's where the barrel rolls over the step. And with just 0.2 and 0.5, the information is insufficient. We need to find the perpendicular distance from the force, right? So we have the perpendicular distance of the force from the pivot, which is this distance, and this is given by, so perpendicular distance for F is equals to 0.5 minus 0.2 equals to 0.3 meters. Okay, next we have to find the perpendicular distance for the weight, which is perpendicular distance for weights is equals to this distance over here. Let me change to red. Okay, is this distance over here. But how do you find this distance, right? So recall using your Pythagoras theorem, this distance here we found to be 0.3 meters. 0.3 meters. And because this is a circle, the radius, or O to the tip of the step, this is also 0.5 meters, or the radius of the circle, right? 0.5 meters. So using that, we can see that this here, this here is O, and this is the tip. So this is 0.5, this is 0.3, and by extension this would also be 0.3. So what is the distance here? It's equals to, let's call this x. So x squared is equals to x squared plus 0.3 squared is equals to 0.5 squared. And solving this equation, you will get x to be equals to 0.4. Okay, so now since we have the perpendicular distance for w, which is x, which is 0.4, equals x equals 0.4 meters, we can use the principle of moments about this point here. So let's call this point, say, point z. So taking moments about z by the principle of moments, sum of clockwise moments is equals to sum of anti-clockwise moments, and clockwise moments is the moment due to the weight, which because it's going this way, right? And the force of the moment due to the force would cause the barrel to rotate this way. Okay, so the weight F times perpendicular distance equals to F times perpendicular distance, and this force is 1500 multiplied by 0.4, which is equals to F multiplied by 0.3. And solving this, you will get F to be equals to 2000 newtons. So this is the minimum force required for this barrel to roll over the step. And that's it for the principle of moments. Thank you.